So chapter 6, we're going to be looking at applications for integrals. So the first application we're going to look at is the area between two curves. So say we have some function f of x and some function g of x, and we want to find the area in between the two. Basically this region S. Thank you. So the idea, what we'll do here is we're just going to start by imagining a bunch of rectangles that we'll use to fill up that area. So we'll have some rectangle with some width delta x, some x on that interval, we'll call that x dx sub I, and then we're going to have this part that's above the x-axis. Well, that's just the value for f of x. And this value that's below the x-axis, well, this is a length, so it has to be positive, and g of x is, if this point is like x comma or xi comma negative, would be like xi comma g of xi, but it's negative. So we'll just slap a negative onto it to make it positive. So the height then of the whole rectangle is just f of x minus g of x. So we'll just say, okay, well, we'll just make those rectangles infinitely small or infinitely narrow, and we'll add them all up, and that should be my area. So I get something like this, where I use the rectangles to do my approximation. Is everybody okay to envision kind of what we're doing? What is it when we're adding up a bunch of these, or infinitely many of these rectangles? What is that called? That's an integral, right? Is that just really what we're talking about is an integral? So the area between the two curves is just the integral from a to b of f of x minus g of x dx. It is important that g is the upper, or f is the upper and g is the lower. You guys okay with what I mean by upper and lower? Or if we integrate with respect to y instead of with respect to x, oops, that's not right. F of x should be the right-hand function, and g of x should be the left-hand function. Everybody's okay with that idea? What happens if g of x is equal to 0? What if g of x is just the function, the 0 function? Would just be the integral of f of x, right? Which is going to give us the area between f of x and the curve x equals 0, which is just the regular old integral, right? What we've been accustomed to doing. So that makes a lot of sense. You guys agree? Okay. So that looks really good. So let's do some examples of just kind of practicing with this. So the first example says, find the area of the region bounded above by the curve y equals e to the x, and bounded below by the line, or by the curve y equals x. And then we're bounded on the side by x equals 0 and x equals 1. So let's set up our integral. This will be the integral from what to what? 0 to 1, very good. Right? We're starting at 0 and ending at 1. My upper function is e to the x, and my lower function is x. So I'm just going to be integrating this. Everybody feel good there? I can just kind of distribute my integral. What's the antiderivative of e to the x? E to the x. What's the antiderivative of x? X squared over 2. And then we'll evaluate from 1 to 0. Everybody feels okay there? And if I simplify that down, I just get like e minus 3 over 2 or something. Yes, Finn? So it's like, it would really be like minus this guy. So like the negative sign distributes through. Is that okay? But that's super simple idea, right? Easy integral to do. Mr. Kulik, can this get harder? Well, I guess. So here it says find the area of the region enclosed by the parabolas y equals x squared and y equals 2x minus x squared. So right away, the first question is going to be, what should the bounds of my integral be? Yeah, so it should be the in between the intersection of them. If that picture wasn't given with the intersections, how would I find those? I can just set the two equations equal to each other and then solve for x. Right? Everybody's okay there? So if that picture wasn't given to you with the intersections, or if the intersections weren't labeled, how would you find them? You just set the two functions equal to each other and solve. Okay, what is my upper function then? Look at the picture. Should be 2x minus x, right? And my lower function should be x squared. And I would probably combine some like terms and pull that factor of 2 out front. We don't have to. Is everybody okay there? No or yes? We're good? Okay. So we can do our antiderivatives. Just like before, the antiderivative of x is 2x squared, or I'm sorry, x squared over 2. What's the antiderivative of x squared? X cubed over 3. We're evaluating from 0 to 1. So I'm going to go ahead and distribute the, it doesn't really matter. We'll keep the 2 out there. So I'm going to have 1 squared over 2 minus 1 cubed over 3 minus 0 squared over 2 plus 0 cubed over 3. So I get here, let's see, I get 2 times 1/6 or 1/3, I think. My mental math is right. Sometimes fractions in mental math is tricky. What do you guys think? It's okay so far? So again, ways that Mr. Kulik can make this trickier is if I don't give you the endpoints and you have to figure them out, it's going to be the points of intersection between the two functions. You can do that just by setting the two functions equal to each other and solving. And that's what we've done in this particular problem, right? The region bounded between the curves x over x, or over the square root of x squared plus 1, and then y to the 4th minus x. Notice that we're not given the points of intersection. Now 1 is trivial to see, right? Just by looking at the picture. What's one of the solutions? It seems like it's 0, right? let's see here. What's going to be the easiest way to do this? What do you guys think in terms of solving? So one way you could certainly do this is to type them into the calculator and just look for the intersection, right? That's totally legit. Doesn't tell you that it's a no calculator problem. And looking at this, I'm not sure that you'd be able to do this by hand, but we'll take it. We'll give it a shot here in a second. Okay, so there's my first function. Then I have x to the fourth minus x is my second one. And I've been using all kinds of crazy windows here in pre-calculus as we've been doing stuff. So I'm going to just do a zoom standard so I can get that window back. So that's the intersection I'm looking for. Second trace, pick the intersect command. Enter, enter, curve 1, curve 2. For my guess, though, I got to move it close to where I think that intersection is, because there are two intersections. So I get 1.18-ish. Now I'm going to assume that that's not an answer that I would have been able to come up with by hand. It looks pretty terrible. Just for the sake of argument, I would start by squaring both sides to get rid of the radical. Then I'd clear the fractions. So multiply both sides by x squared plus 2, and there's going to be a lot of terrible foiling. And we'll be left with some huge degree polynomial that I'm not going to be really excited about trying to solve by hand. I don't know that it'll really be doable to solve by hand. Just kind of eyeballing that. All right, so my area then is going to be the integral from 0 to this 1.18. And then what's my upper function going to be? Good. And my lower is going to be that guy. Oh, thank you. Yep, that makes a big difference. Why does that make a big difference? Yeah, this is the antiderivative of. Do we remember? Is this an antiderivative? Sine inverse, you think?
Yeah.
Let's go back and double check. Sometimes that escapes me also. I just want to go here. No, it's 1 over 1 minus. Ooh. Uh-oh. Where are my inverse? Trigs. They got to be somewhere. Oh, they're implicit maybe. There they are. Okay, so I don't actually have one for this, right? Uh-oh, what should I do? Yeah, use substitution. Sounds like an excellent idea, the person that mumbled it. Where did you go? Right here. So what should my u be? X squared plus 1. So my du dx is going to be 2x. So du over 2 is going to equal x dx. No problem. Thank you. So this is really going to be Everybody's okay with how I'm picturing that first integral? Okay, so what's the antiderivative of 1 over the square root of u going to be? Remember, that's like negative 1/2. So it's u to the 1/2 over 1/2 plus 1. And then I have still that times the 1/2 there. And then I'm going to write this, but we have to put the x's back. Oops, not 3. So far, so good. So then I got to put my x's back. Now this is 3 over 2, right? Down here. When I multiply the half in, that just becomes a 3. Oops, dropped a parenthesis there. There we go. And then it's just like calculator time, right? At this point, we're just plugging things in. It's okay for me to stop here. We did all the hard parts, right? Okay. What happens if one curve is not always on top of the other? Like, look at this picture. G of x is the blue one, f of x is the pink one. What are we going to have to do? Yeah, that's going to turn into 3 separate integrals, right? So I'm going to have to do this as S1 plus S2 plus S3. So the integral from, like, we'll call that C and D there. We'll go from A to C, and there the f of x is on top. And then from C to D, the g of x is on top. And then from D to B, the f of x is back on top. Everybody's okay with that? So, fine. What's going to be the hard part? Going to have to solve for C and D, right? To do that, you're just going to be setting the two functions equal to each other and solving. Feel okay so far? Okay. The alternative here, if you're going to be able to use a calculator, is that you can just do an absolute value to it, and that'll give me the same thing. If you have to do it by hand, though, these are really the same ideas, right? Okay. So let's say we want to find the region of, or the area of the region bounded by the curves y equals sine x and y equals cos x between 0 and pi over 2. I notice that they switch, which one is the upper and lower, at pi over 2. So my area is just going to be like A1 plus A2. A1 is going to be the integral from 0 to pi over 4 of cos x minus sine x. And then we'll have the area 2 is the integral from pi over 4 to pi over 2 of sine x minus cos x. again, this is the same idea as if I did just the integral from 0 to pi over 2 of the absolute value of sine x minus cos x. But if I had doing this by hand, I'd have to break it this way anyway. So usually I don't even bother with the absolute value unless it's like a calculator multiple choice question where, okay, I'll type it in with the absolute value, no problemo. But if I got to do it by hand, like, usually I don't even bother writing the absolute value. Is that okay with you guys? You see what I'm saying? What's the antiderivative of cosine? Sine. What's the antiderivative of sine? Negative cosine, right? And then the same idea here, right? So I'm going to have sine of pi over 4 plus cosine pi over 4 minus sine of 0 plus cosine of 0 minus cosine of pi over 2 minus sine pi over 2 plus cosine pi over 4 plus sine pi over 4. Okay. Sine of 0 is 0. Cosine of 0 is 1. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. So those guys, because I have a plus and a minus, those just cancel out. Everybody's good there? Sine of pi over 4? Root 2 over 2, and same with cosine of pi over 4, right? So we have 1, 2, 3, 4 root 2's over 2, or just 2 root 2. Feel okay? I ripped through that pretty quick because we're good at trig. Very good at the unit circle still. Again, if you're not there, like, it's okay if you just have quadrant 1 memorized and are reasonably good with your imagination of like, okay, if it's same thing, now we're just in quadrant 2, so this is negative or that's negative. Like, that's enough. Michael?
Do you explain like how it's the same when you're doing a calculator as the absolute value? Like,
Yeah, so the reason that we had to flip is because if we didn't, that area was going to be negative, right? But if there's just like an absolute value around it, it's going to have it just turns that area positive, and then we add it together, and it's going to be the same thing as if we didn't flip it, or as if we did switch the direction, so we ended up with a positive area. Does that make sense?
Yeah.
So that's the whole idea, right? What we did was the same thing we'd have to do with the absolute value, just by flipping it, make sure that it's, that the area is coming out to be a positive value instead of a negative. All right. What if our functions are not written with x as the independent variable? So some regions are best treated by regarding x as a function of y. If a region is bounded by curves with equations x equals f of y and x equals g of y, with some y equals c and y equals d, like those are going to be your bounds of integration. So that's like the picture we have here, right? X equals f of y, x equals g of y, y equals c, y equals d. So it's defining that region there. Well, its area is just going to be the same thing. It's going to be the right-hand curve minus the left-hand curve. So we're really talking about still building the same kinds of rectangles, just they're going to be horizontal instead of vertical. It still becomes an integral, but now it's with respect to y instead of with respect to x. x. So it's nothing has changed. So it says find the area enclosed by the line x or y equals x minus 1, and the parabola y squared is equal to 2x plus 6. Now, this one screams out as a candidate to integrate with respect to y instead of respect to x, because get to y by itself involves me having to make like a plus or minus. I don't want to do that. That seems like a big, gigantic hassle. That scares me because I'm not really sure what to do with that. So I'm going to start by just getting these things as x equals. So for the first one, I just add 1 to both sides, and I have an x equals equation. For the second one, I have to subtract 6 and then divide by 2. Now I'm going to have to find the bounds of integration. So I'm going to set these two things equal to each other. So what kind of an equation do I have here? It's quadratic, right? You see the y squared and the y to the first are my only variables. To solve a quadratic, I want to get it all onto one side. It has to equal 0. So I'll subtract the y over and then subtract the 1 over. And then I would probably multiply both sides by 2 because I do not like that fraction in there if I don't have to have a fraction, which I don't. I'd prefer not to. And then I could either factor this or try using the quadratic formula. Does this factor? Yeah, just y minus 4 and y plus 2. If you missed that factoring and just went straight to the quadratic formula, that's no problem there. But do you have to have that memorized? The AP expects you do, the quadratic formula. So far, so good? So I know I'm going to be doing the integral from -2 to 4, but which one is on the right and which one is on the left? Well, let's sketch a little bit of a picture about what this is going to look like. So the line y equals x minus 1 is just going to look like that, right? Everybody agree? The parabola x equals y squared minus, or y squared over 2 minus 3. So which way does the parabola open? Left or right or up or down? Because it's a x equals, it's going to open left to right or right to left. Everybody agree? Which way is the opening? Because the y squared is positive, it should be opening to the right where the positive x's live. Everybody agree? What's going to be the vertex of this parabola going to be? Just -3, right? It'll be x equals -3. But it's going to look like that. Does that feel okay with you guys? And how I was able to sketch a picture without having actually plotted anything, without a calculator, just knowing what I know about parabolas. So this is the region I'm looking for. I'm going to be integrating this way, though, left and right. So this is my lower bound. That's my upper bound. So that's 4, and that's like -2. Is okay? The function that's on the right is x equals y plus 1. And the function that's on the left is the y squared over 2 minus 3. Is everybody okay with my setup there? So it's always right minus left.
You get the y plus 1 in.
Right? That was the first thing I did, was rewrite my equation so that they were x equals. Does that feel good? Okay. Now I would probably clean that up a little bit to make the integral a little bit less complicated. Does that look okay there? I just combine some like terms. So far, so good. And it's easy from here, right? We're just plugging in and evaluating the rest of the way. If I wanted to do this on my calculator, how would I do this on my calculator with y's there? I'm just calling them all dx. I'm just using x's instead of y's on my calculator. Give me the same answer, right? Like if, like the integral of f of x dx is going to be the same as the integral of f of y dy. It's fine. All I'm doing is changing the name of my variable. The integral is going to be the same. So if you're trying to use your calculator to do that, it doesn't matter. Now the picture, making sure things are on the correct sides and everything, that you have the right minus left set up. Calculator's hard, doesn't help you much there. What do you guys think on this idea? This is like the easiest thing we do in chapter 6, so this should feel pretty doable right away. It's basically just one formula and just doing integrals just like we've been doing. While you're doing the homework, will you run into a u sub? Yeah, sure, we saw one in the homework, right? Will you see things that have to be written in terms of y's or in terms of x's? Yeah, right? Seeing things where we have to integrate with respect to x or integrate with respect to y, both those things will happen. Will you see things where it makes sense to simplify before you integrate? Oh yeah, we just did that, right? That made that problem quite a bit easier to combine some like terms before I integrate. Please make sure you're trying to do that, or at least checking to see if you can do that beforehand. But this is the basics. Next section, we're going to be computing volumes. Actually, the next two sections are volume problems, which is quite a bit more difficult unless you have very good imagination. If you have very good three-dimensional imagination, it's much easier. And we'll talk about like how to start building that, and what are the ways around it once you get comfortable with like what you're doing. Can I do this without having to imagine the three-dimensional structure? And what to look for in 2 dimensions, it'll tell me what I need to do. We'll get there, but I think it helps to start trying to picture things three-dimensionally, and that'll be next time. So if you want to bring your imaginations with you, your spatial imaginations, can be really quite helpful, at least in the setup stages, about selecting the right type of shape that we're going to be building our three-dimensional region out of. Because there's 3 options. So you have to be able to choose the right setup for the specific shape. So being able to picture what you got in your head helps. But that's for next time. What do you guys think? Was this okay? Today felt all right? pretty clear as to like what's going on and how it works and what you got to do. Okay.